observation function in two limits. When the diffusion time across the observation volume is much smaller than the reaction time, which is, they are defined here, or when in the other situation, when the reaction time is much smaller than the diffusion time. So we obtain, this is in the fast diffusion limit, which we think is the one that applies to the case of the binding sites on DNA, and we obtained expressions beyond the asymptotic limit. And so let me give you some figures of the ratio of the variance of the average with respect to the initial variance of the stochastic variable for the case of the occupancy of the binding site in different regimes. And what's in this very black thick line, that's the computation of our analytic expression, and the dashed dotted line is the asymptotic thing. So that, for example, in this very extreme case, what we see is that you can achieve a, oh, goodness, let me see. This is too bad. Because I don't know. There. So that we can achieve a very huge decrease in the variance of the average even faster than than when the asymptotic regime kicks in. But in any case, in order to analyze how good our expressions work to describe how fast the error decreases, we used another set of experiments in which what they do was, this is again Gregor, they observe the transcription, the instantaneous transcription. What they do is they have a fluorescent tag that they observe as the messenger RNA is produced, so that you can see the fluctuation in the transcription process as you make the mRNA molecules. And also they measured how fast those initial fluctuations in the produced messenger RNA decreased to a certain level after what time. So that's what they observed, and they saw that temporal averaging was not good enough. So these are what they do here is they looked at another type of molecule. No, it's not bicoid, but it's pretty similar. And these are the experimental points. This is the noise as a function of how much the noise in the average RNA that has been produced after a certain amount of time. That is how much accumulated RNA you have. And this is given the initial noise, if you think that you are averaging over time, where that error would go to, which is way above what the cell is doing. And so, well, again, you have time average, the variance is the same kind of thing, how you measure the noise of instantaneous transcription and the noise of the accumulated mRNA. And so, what they said again was, well, in order to explain this thing that is doing better than time average, we need some spatial averaging. And so again, we try to look at this problem, again with the same stochastic variables, etc. And the thing that we saw, let me give you, this would be the variance of the occupancy initially. So it's the stochastic variable, it's whether it's occupied or not, the binding site that we are observing. And that's the relative error squared, variance over mean squared. And then you produce the messenger RNA, and what we look at is actually the average of the occupancy, that we think it's like a proxy for how much a messenger RNA you produced. And so the variance divided the mean squared of the average is this error. And what we observe is that the variance here, this error, starts with this error. Oops, goodness. Starts with the error of the stochastic variable and then decays, well, with 1 over the observation time eventually in the asymptotic regime. But the thing is that the initial variance of the occupancy depends on a stochastic variable, which is the free molecules that are going to bind. So that this probability of binding is some sort of stochastic variable itself. And so if we include that, so we assume that the variance, initial variance, is not just because binding and binding of the binding site, but also we superimpose the variance of the things that are coming in and out, which so far have been assumed like a constant concentration, like a rate of coming. Well, we did that in a very simple way, and we added, let me see. So what we did was the following. We say the binding probability we estimate in terms of the average of the free molecules that are going to bind to the binding site. So we have an estimate of the binding probability. But then that estimate is going to decay with the characteristic time with which the average of the transcription factor number of molecules decays in time, which is related to the diffusion coefficient of the transcription factor. And so we did a very simple thing. We said, well, the variance of the occupancy is related to the original variance due to the mean occupancy, or the mean also number of free molecules, plus some variation of the probability of binding, because the transcription factors are very fluctuating. And we did some propagation of error. And so basically what we are saying is that the initial variance has like two components. One is related to the binding and unbinding, and another one is because of the fluctuations in the molecules that bind to the binding site. And by doing that, well, we put the numbers that we had got for the diffusion coefficient from BCOID, the KD also that we got from the analysis of BCOID, etc. And we could explain the decay in the noise pretty well. So this is the noise that we get in the accumulated messenger RNA, and this is the noise we would have got if we hadn't taken into account that the initial variance is not just due to binding and unbinding, but there is another thing because the transcription factor is fluctuating in the vicinity of the binding site. So basically what we say is, this is the computations beyond the asymptotic limit. To the right is the asymptotic limit, to the left is the whole time. And so basically what we are saying is that there is a spatial averaging that is explaining this reduction in the noise, but it's the spatial averaging not of the messenger RNA, but of the transcription factor. So before you have a huge fluctuation, then that decays goes very fast to some mean due to the fast diffusion of the transcription factor, and then it goes further down because of the binding and unbinding, the noise. Okay, so this is the message of this thing. And so in summary, this binding and unbinding is used to make decisions. In this case, it would be whether you express hunchback or not. And so you have this reading process that is highly fluctuating, and you can achieve a good readout after a certain time due to some sort of averaging. And so this reading depends on diffusion coefficients, so we worked on that. but also, so it's important to interpret correctly what diffusion coefficients you get from the experiments, but also it's important to understand what's the nature of the initial fluctuations to see what's the time scales that characterize the decay of those initial fluctuations in time. And that's the thing that we are working on now with these experiments to quantitate the diffusion coefficient of calcium. What's the initial fluctuations to understand what's the nature of the correlation times that we obtain from the experiments. Okay, and with this I finish. Thank you.
Questions, comments? So I actually have a, okay, so if I understand correctly, you have this sack of nuclei.
Yes.
And bicoid comes in and starts diffusing. And the bicoids they measure are inside the nuclei, right?
They measure, they do experiments both in the nuclei and also they do during mitosis. They measure, they have experiments in different situations.
So the spatial averaging they're talking about is over nuclei, essentially.
Yes, it's like you have, the thing is, bicoid is produced at one end. It diffuses and it's degraded, and that's why you have that spatial pattern, which is a gradient. Then at each distance from one end, you have several nuclei that are sort of exposed to the same constant. If there were not fluctuations, it would be a bunch of nuclei. Imagine that the way I think of it, you have the embryo like that, and when they are in the border, the external border, it's all these nuclei here are sort of exposed to the same concentration of bicoid, sort of, because the gradient goes from one end to the other. And so all these nuclei here are exposed more or less to the same concentration. And when they do this averaging, they say, well, if I think that so many, the RNA, messenger RNA coming from these many nuclei I do the average over those things, then I reduce the noise. But the thing is that you cannot guarantee that the messenger RNA comes from the same plane perpendicular to the axis, which of course they are going to mix up when the nuclei break up, because you have all these mitotic processes, and so the nuclei break up, all the stuff gets into the cytoplasm, then they get reformed, and then you have the gradient reestablished and all the distribution very fast. That's the 3-minute thing that they measure in this more recent thing. And so the thing that we think of is that actually what you have is this bicoid, maybe in different nuclei that should be exposed at the same concentration is very different because of the sites see different things. So, but then it takes some time, which is pretty short, to come back to some mean concentration that each binding site has been exposed to. And then so that initial fluctuation has the two sources of fluctuation. And then it decays with this time average of the binding process, assuming that you have mean concentration of bicoid that corresponds to that position. That's the idea that we have.
Bicoid is a transcription factor.
Yes.
Okay, so the maternal input is the transcription factor or the messenger RNA?
No, it's bicoid.
The protein?
Yes.
Ah, okay. Okay. No other questions?
Well, no, it's the messenger RNA of bicoid.
Of bicoid.
Which is distributed mostly on one end. So you have this. So you have the messenger RNA that comes from the mother of bicoid, and then bicoid is produced there all the time, and then it diffuses and it's degraded.
Yeah, okay.
That's the thing.
As a protein.
Yes, as a protein. Yeah.
Okay, thank you. There's no other question?